My name is Daniel, and I'm a junior.
I'm Andrew, and I'm a junior.
I'm Cyrus, I'm a junior.
I'm Katie, I'm a junior.
I'm Jaden, I'm also a junior.
Good morning, everyone. We're here to present to you The House Always Wins. Before we dive in, I just want to highlight how technical computing made our work possible. First, we ran over 100,000 simulations, which would be near impossible to do by hand. Second, we were able to store massive data sets in our code, which made it really easy to cross-check things. Third, our code uses if-else checks to match multi-phase behavior logic. And fourth, we made visually accessible heat maps and graphs. Fifth, we reran our model 5,000 times with randomized inputs to test sensitivity.
The introduction of online gambling has made this form of entertainment more accessible than ever before. Currently valued at nearly $90 billion, the market is projected to surge past $150 billion within just 5 years. However, studies from the American Psychological Association highlight a darker reality. This accessibility comes with significant harm, including addiction affecting up to 110 million adults worldwide and severe financial debt compounding to tens of thousands of dollars. In our model, we aim to identify who is most likely to gamble and analyze these real-world impacts across 3 distinct parts, from calculating disposable income to tracking behavioral cycles and finally measuring long-term societal impact.
And that brings us to Q1. To understand what people lose to gambling, we first need to know what they can afford to spend, otherwise known as their disposable income, based on their age, salary, and other information we deem to be relevant. We made 4 key assumptions for Q1. First, we eliminated it to 6 essential expenditures, these being housing, food, healthcare, transportation, education, and childcare. Second, we assumed that housing follows an angle curve and that healthcare follows a J curve. Third, no major financial shocks occur during the year. And fourth, we assume that every filer is a single filer. We built our model around 3 key lines of reasonings. First, the fact that disposable income depends on who you are. A 28-year-old and a 50-year-old with the same salary do not necessarily have the same disposable income due to different circumstances. Second, we should subtract only essential expenses and not just taxes. Third, it has to be flexible enough to handle both the United States and the UK systems. And here is our model. Real disposable income equals effective income minus taxes minus essential expenses, all divided by 1 plus the sales tax rate. The S-star effective income is a primary salary plus the expected value of money from a second job, which is the probability that someone actually has a second job multiplied by the average side income for their education and age. Then we subtract total taxes and essential expenses across our 6 categories that we detailed earlier. And finally, we divide it all by 1 plus the sales tax rate to convert nominal dollars into real purchasing power. So here is an implementation of our model. This loop runs through hypothetical profiles that we made earlier to compute all components of the model and return a disposable income for each profile. Now, zooming into how we modeled each essential expenditure, housing uses an angle curve, healthcare a J curve, education a loan payment formula, and each form matches exactly how they would work in real life. Andrew, do you want to add anything?
Yeah, to round it out, transport is a weighted mix of car and transit costs based on whether you live urban or rural, and childcare scales with region, income, and number of kids. And each category gets multiplied by a regional price parity, so $1 in Manhattan is not equal to $1 in rural Ohio. Moving to taxes, which are the largest mandatory deduction from gross income. Our model calculates federal tax, payroll tax, and state taxes. We took a step further with state taxes by programming the distinct tax structures of all 50 states.
For example, we implemented state taxes with a switch function that handles zero-income states, flat rate states, and progressive bracket states. We validated our model against the Bureau of Labor Statistics Consumer Expenditure Survey across 7 age groups. Our model achieves an R-squared of 0.82, a correlation of 0.97, and just a mere 13% mean error, meaning we capture the life cycle shape of disposable income almost perfectly, with some level bias. The model undershoots working ages slightly and overshoots 65 plus, where post-Medicare healthcare costs spike behind our J curve, but since Q2 and Q3 focus on working age gamblers, we are very confident that these work as good inputs. Here, we ran our model on the 12 US profiles mentioned earlier, spanning from a salary of $15,000 to $185,000 across 9 states. The high earner in California keeps 45% of her income with $83,000 left over. But the interesting thing to note is that the single mother in Georgia and the adjunct professor in Massachusetts come out negative, meaning they can't even cover essentials based on their salary. These two profiles enter Q2 with a zero gambling capacity and are very, very vulnerable. Here, we ran the same models on the UK, but unlike the US, all UK models were positive, and this is largely due to the fact that the National Health Service in the United Kingdom essentially erases the need for healthcare expenses. Now zooming out from individual profiles, we map disposable income across every age and salary combination for a single male in Ohio that has a bachelor's degree. On the left, the dashed line marks the point where anyone below it can't cover essentials. It raises with the age because healthcare gives more expensive and then dips at 65 when student debt clears. On the right, the UK break-even age is roughly 30% lower at every age.
To understand how sensitive our models to each input, we ran a Monte Carlo simulation with 5,000 iterations. We varied each parameter by 10% to see how the model reacted. As you can see here, salary is predictably the largest driver of disposable income. However, looking at the expense categories, food and housing cause the greatest variance. This confirms that our results mirror real-world household budgets. This is the MATLAB code, where we perturb each parameter randomly across 5,000 iterations and compute the standard deviation of disposable income. And to close out Model 1, our key strengths are flexibility and validation. The model covers both US and UK populations in detail and is validated against BLS data. On the limitation slide, we slightly overestimate disposable income for the 65 plus demographic due to Medicare not being modeled, and we apply a universal standard deduction rather than itemized. But these are known constraints, and the model still provides a robust foundation for Q2 and Q3.
Thank you, Andrew. Q2 asks us to take the same factors that were used to determine the disposable income in Part 1 and generate the expected gain or loss for an individual through sports gambling over the course of 1 year. We tackled this problem through a Monte Carlo simulation. The three key assumptions that we made can be seen here. Firstly, the assumption that gambling volume relates directly to disposable income allows us to discard expenses like loans that would basically be impossible to simulate. Secondly, we assume that gambling participation follows a log normal distribution, creating a light betting majority and a few high-volume gamblers called whales. Our last assumption comes from a desire to model a change in betting behavior or loss chasing. For simplicity, we split the year into two halves with the second half behavior adjusting based on the outcomes from the first.
There are a couple of things that we had to consider while developing the model. The two main ones we focused on being this dynamic behavioral feedback and the uneven societal distribution of gambling activity, and the way that we handle these will be explored as we run through the model. So here's a table of the variables that we used along with the different adjustable weights, and this is organized based on the 3 different layers that our model goes through.
This is our first layer of the model, which uses demographics of an individual to determine their baseline wager and gambling intensity. The legality sigmoid function accounts for underage gambling. The demographic factor FDemo accounts for gender, age, and education with weights derived from a survey done by the Siena College Research Institute. The intensity factor I is determined by the demographic factor along with the log normal random distribution adjusted by the constants mu and sigma to simulate different types of gamblers. The ultimate goal of this layer, wager amount, is given by the product of disposable income and the intensity factor. Layer 2 aims to determine the betting behavior of an individual. Effective bet count is scaled relative to the rest of the population with a mean bet count among adults of 104. Then we determine the risk preference factor, which tells us what types of bets an individual prefers, such as riskier parlays or simple straight bets. We factored in age and gender using a sigmoid function to calculate this value. And lastly, we calculate the expected return per dollar, capital R, for each individual based on their effective bet count, risk preference, and determinant house edge using a normal distribution.
Right, so layer 3 is where we actually run the simulation in MATLAB. So we start by assuming for the first half of the year, an agent wagers half of their annual wager. Their mid-year income is then calculated based on the agent's initial first half wager and the return per dollar calculated from layer 2. If this mid-year income breaches the quitting threshold defined by the equation on the top right, the agent will not continue gambling in the second half. We also define a performance ratio, theta sub I, based on this mid-year performance, which helps determine the agent's second half behavior. So this is exactly how this second half wager is updated according to the first half outcomes. It's a function of the following factors. So firstly, the risk preference factor, which is updated according to the major performance ratio. A negative theta sub I indicates a net loss, causing an increase in risk preference and therefore an increase in wager amount, simulating loss chasing. And a positive value, on the other hand, indicates profit, resulting in a lower risk preference as the agent tries to protect their earnings. Second, the tilt sensitivity parameter, which is a factor determined by empirical risk preferences based on age and gender taken from survey data. These two factors are applied as vectorized updates across the population array, which is more efficient for large N, and the second half wager is calculated, which is then used to determine the net phase 2 income. And the annual net income is a simple calculation of the sum of the net incomes of each phase. And here we have the MATLAB code used to initialize a population of 100,000 individuals. As you can see, it randomly generates and assigns each agent an age, gender, and education value with distributions based on survey data. And it runs through the loop 100,000 times. And here's the MATLAB code that we use to run the actual simulation.
We use MATLAB to produce graphs representing important data from one simulation. Over here, you can see the difference in profit and loss over the different demographics that we took into account. One thing to note is that the median is much lower than the mean due to the large majority of non-gamblers and the whale skewing the mean value. Over here is the distribution of active gamblers across the different demographics. And this graph over here shows the distribution of each gambler's net return. The scale of this graph is to the magnitude of 10 to the 5th due to the inherent distribution of gamblers as well. The massive spike you see in the middle is to the left of the breaking even line, showing that a majority of gamblers will lose money eventually in the long run.
And finally, we analyze the strengths and weaknesses of our model. So the standard method of modeling gambling outcomes is using a weighted binary coin flip. In comparison, our model accounts for unique individual risk preferences and betting volumes, as well as behavioral changes in these throughout the course of 1 year. However, this is still an oversimplification of real human behavior. The linear behavioral updates that we use don't truly align with real human psychology. And additionally, we rely on the assumption of independent betting outcomes and the exclusion of professional gamblers.
Thank you, Katie. So question 3 asked us to quantify the financial impact of online sports gambling in a way that's understandable to the general public. Our approach was to model not only what gamblers lose today, but what those losses mean for their long-term financial trajectory. So before getting into the model, we made a few key assumptions. We hold the annual loss fixed at the value from our Q2 simulation, so the question focuses on long-run impact rather than short-run variability. We also assume that after quitting, individuals direct 50% of their real disposable income towards recovery. In addition, assets grow at 7%, which is the real return on the S&P 500, and debt compounds at 22% APR, which matches the US median credit card rate. Finally, we use 65 as the fixed retirement benchmark to allow a fair comparison between profiles. Now on to the considerations. We think the two main requirements are that it must be interpretable and actionable. By interpretable, we mean understandable to non-expert policymakers and the general public. We chose 3 questions a person would ask. How bad is the harm right now? What does it cost long-term? And how long does recovery take? By actionable, we mean the metric must enable specific intervention like recovery time and age-sensitive metrics. Our model produces 3 outputs. Metric 1A is the burden ratio beta, which measures gambling losses over disposable income. Metric 1B is recovery time, the years required to rebuild after quitting. And metric 2 is missed wealth, which captures the long-term opportunity cost. Starting with burden ratio beta, it normalizes loss against what somebody actually has available. The equation is simply annual loss L over the real disposable income that we get from Q1. Beta at or above 1 is the exact point where gambling starts to accumulate debt. For metric 1B, it is recovery time. Recovery time converts the financial loss into a metric of time, which is what the general public would want to know. It's the sum of 2 components. End debt, the years needed to pay off the accumulated debt, and end wealth, the years needed to then rebuild that wealth. DT is the debt balance accumulated during the gambling years, which the recovery process then has to clear before any wealth rebuilding can start. The important factor here is the debt spiral condition, where if annual savings are less than the interest accruing on the debt, then recovery time will become infinite. So to combine these, we combine these into what we call the GIS, or the gambling impact score. We normalize each metric to a 0 to 1 scale, where the burden ratio is divided by 1.5 and capped at 1, and debt exposure is normalized against 5 times disposable income. Finally, total recovery time is divided by years remaining until retirement. We weighed recovery time at 0.4 because it was the most important part of the 3, since it captures both severity and duration, with burden ratio and debt exposure each weighted at 0.3. This MATLAB block shows the implementation, where the key parts are the loss ratio calculation, the recovery burden, which handles the infinite cases, and the weighted sum. Here are 6 representative profiles from our model. We can immediately see the pattern. The young male at age 21 has a GIS of 34, similar to the mid-career male at 50 with a GIS of 39. However, the older man loses twice as much per year. That's because the 21-year-old has a much longer time period over which losses compound. That brings us to metric 2, which is missed wealth. The visible cost of gambling is what you lose today, but the cost that matters is what those dollars would have compounded into by retirement. The equation has 2 parts: the future value of T years of annual losses at 7%, and then it grows that value to 65. Here are the results of metric 2. We hold disposable income, annual loss, and gambling duration constant, and only change the starting age. An 18-year-old who gambles $6,000 a year for 10 years forfeits over $1 million, while a 50-year-old who does the same exact thing only forfeits $116,000. That's almost a 9 times difference for the younger person. And this is the core compute recovery function that simulates each year of gambling, tracks debt accumulation when losses exceed income, and calculates end debt and end wealth. Lastly, our strengths and weaknesses are that, first, our model combines income and losses into a single long-run impact measure. However, it also ignores real betting variation, and our use of fixed financial rates simplify post-quit behavior. That is the end of our presentation, and thank you for listening.
Does anyone want to kick us off?
Sure, thank you very much. You guys were going like 2 times speed on my setting here, but my brain caught up, I think. All right. It's like turning in a paper with 10-point font, just to cram everything in there. But, okay, so loss chasing and things like that. If you had more time, what do you think you could have done with looking at loss changing and other behavioral patterns too?
So
in
the
your
main
model?
limiting factor in our loss chasing model was that we automatically assumed that an individual who loses in the first half will like double down on gambling in the second half, while in reality, some people will go back on it and take less risks in the second half. We decided not to do this because, well, first of all, we couldn't find a lot of available data on individuals who wouldn't loss chase. And second of all, based on, I believe it was called the prospect theory, individuals feel the weight of losses much heavier than they feel the weight of wins. So therefore, they'll feel like a greater emotional need to chase after these losses and make up for them by doubling down.
I said to the previous team, through this, I'm learning some of the terms. Is there something else other than loss chasing that you would have incorporated into your model?
We kind of simulated a little bit using our dynamic threshold of quitting. So basically, we assume that if an individual loses too much in the first half, they just quit entirely in the second half. Because this is like an oversimplification though. Like if we had more time, we would have loved to like make the threshold like even more flexible to incorporate people like going lower risks in the second half.
Okay. Thank you.
I have a follow-up question because you mentioned like it's difficult to find data to necessarily pin down the numerical impact of these behaviors. One place you did mention that you had data was you have these multipliers for, I believe it's gender, age, and there was one other variable that sort of impacted gambling intensity. And I want to understand what was the data you found and how did you map that to these multipliers?
We mainly had 3 data sources. One that M3 provided us, YouGov survey and Siena Research Institute. Can you go back to the slide with the gambling intensity? Sorry, this is taking a long time. So FDemo, we basically, there was data that gave us splits for the percentage of gamblers and their profit loss margin, the percent that were profitable. And we basically, to put it shortly, we trial and errored until we found values that were, I think we were within 10% of the actual values.
So you sort of like tune these parameters to match a table. Okay, that makes sense. And then can you just give us a sense for interpretability? Like what, was it highly varying? Like did the demographics have a big impact on the model? Were they sort of close in terms of how much people gambling intensity was?
Yeah, so actually our simulation graphs show this very well. So as you can see, this is the distribution of gamblers, active gamblers in our simulation. So it shows that more people who don't go to college are more likely to be gamblers, as with males opposed to females. And we found that the middle-aged people, like 30 to 40 years old, are also more likely to gamble.
Okay, makes sense. Thank you.
Can you go back one page, please? So on here, did you look at the variation that you were seeing in your simulations to generate these final plots?
Wait, sorry, could you repeat that?
So this is results from your simulations. Are these just plotting the means from the simulations?
Yes, this is mean and median value for each demographic group and their profit and loss for the year.
And that you have an idea of the variation that you would see in this if you ran different simulations?
Yeah. Wait, what?
Like, was there a lot of variance in these simulations or no?
No, yeah, that's why we only decided to put one simulation on the board because the rest of the simulations were pretty similar to our first one. So, like, if we put more than one, it would just take up space.
And can I ask a follow-up while we're looking at this page? Can you interpret for us why is the median so different from the mean?
This is because of the log normal distribution of the gamblers. So basically, it's like there's a very large clump of values, like lower wage values, and then there's a very heavily skewed right tail. So this means that while the median is like pretty low because most people only partake in gambling very lightly, the median is quite high because the mean is quite high because of these whales. They're skewing the data. Like there's only a few percentage of the population who's able to bet this heavily, and they're skewing the data. Yeah.
Yeah, that makes sense. Thank you. Any other questions? Okay, thanks, guys. We appreciate both the presentation and the thorough answers. You have 1 minute to say any thank yous of your own.
Oh yeah, so firstly, we would like to thank our friends and family for their continued support. Of course, we would like to thank our coach, Mr. Honor, who has guided us throughout the year. This is our first year of modeling, so he has taught us a lot. And finally, we would like to thank M3 and this association and the judges as well for providing this opportunity for us. And yeah.